Yeah. Okay. So am I audible now? It's fine. Okay. Yeah. So I'd be basically this is the problem. I don't know what that is. Okay. Now it's fine. Okay. So yeah. So what we're basically talking about the big data available in astronomy, and so my talk would be the basis for it. What we are going to talk about. I'll talk to you about some of the data sources, but later on we'll go into detail with each of them as we come along, right? So you'll have all heard this big thing about big data, right? Anywhere when you're walking on the streets, there's all these data scientists, and the highest paid jobs are what data scientists get, right? Uh, my son also studied from University of Hyderabad, and when he finished his master's in mathematics, his whole class, excluding him, everybody went in for data. They all became data scientists. He was the only one who then went in for a PhD program. Remaining everybody became data scientists, and I'm sure that while he will still take some time to set himself up, a lot of these others have set themselves. So agreed, there's a lot happening about data science, and the important thing that even astronomy is also a part of it. Obviously, this is not going to be this is not the money making thing, but we have been doing this thing since some time about teaching students about data analysis and all that. So one thing is, you may do it for the love of science, that you actually learn data science because you want to study astronomy and data sets and things like that. But on the other hand, there's also another important thing, that this can be in principle applied to anything. You could apply this to industry, to the sales of cars, to shares, to whatever you want, right? As long as you understand the concepts, if while you are doing your PhD or whatever research you do, if you understand the concepts behind how you're handling data, what are you doing with stats, how do you look for patterns for various machine learning techniques, etc. If you understand that thing, those principles can be applied to anything. Because a long time back, I always thought that I should make everybody an astronomer, right? And then I think I slightly matured, became wiser with time, and I realized that probably that's not the right approach, that you want to make everybody an astronomer. Not everybody needs to be one. They can opt for this thing, but astronomy can teach you the vital skills which you can then apply to anything else, right? So depending upon your requirement, your interest, your understanding, you may actually apply it to something. So part of the workshop is, yes, it is for astronomy. Our life is for astronomy, no doubt about it. But in principle, if you understand these the 4 days what we are going to do about coding, etc., you can definitely apply it to other fields or other things that could interest you, right? So that's another thing which you can apply. So let's see what is basically big data. Now, one second, I'll just this thing. Yeah. So big data, you're hearing a lot about it. So even Rita spoke to you about that earlier. Astronomy was what was called data poor science. We hardly had any data, and therefore people often made jokes about the kind of statistics also that astronomers made, because you barely had 2 objects, 10 objects. Based on that, you made some, some these things. But now in astronomy, it is actually a data-rich science, because like Rita told you, you have so many of these missions, you have terabytes of data coming out, petabytes of data. There's so much of data available through these various sources that now the whole approach in astronomy has changed, right? Earlier, we deal with small numbers. Now you have big numbers. So basically now we also need to study big data, because these are giving us different ways to analyze, extract. First of all, you'll see through our tutorials, we'll show you how do you actually extract information from catalogs. You can directly use your Jupyter notebook itself to extract information. And actually you can look at, you can't use all the traditional data processing software. You need to use slightly more, software which is more usable with large data sets, because of this complete change in paradigm, that you have to now deal with big data. So what is the basic V's, 5 V's of big data? First of all, the biggest problem is volume, right? So we'll see how do people actually handle volume, right? If, for example, you want to query a database, right, and you download the data locally on your system, that's actually not doable, because number one, the data is too much. It will take too long for you to download. And if you want to query it, then it would not be effective at all. On the other hand, if you do it all on the fly also, if you do it through the net, you will obviously, the queries will take too long. So now most astronomy data sets, what happens is you can become a user. So you get a login on the server which has the data itself. You actually get a login on the server. So many of the servers give you 1 GB, 10 GB, whatever space. You can request more also if you want. And you basically query the data from the server itself, where the data is sitting, right? So that is one of the smart ways of handling these big volumes of data, that you get a login onto the server which has the data, you query it over there, and then you retrieve only what you want, right? So whatever conditions you put on the data, everything will happen over there, and you get it in that way. The other very important thing is that many of these data sets, because they are run through pipelines, they are basically pipelines which process the data. Therefore, what is very important is the accuracy and quality of the data. Because like I specifically, I'll be talking about Gaia, Kepler, TESS. In all these data sets, what happens, you have these pipelines which give you all the results. The pipeline doesn't do anything about filtering or sorting the data. It gives you the details about the data with the errors, etc. And then it is up to you, as part of your code or whatever, to check on how good or bad that data is, so that you filter it. So therefore, the accuracy, the veracity, or the accuracy and quality of data also has to be handled by your code. There's also a variety of data, so therefore you could have, we'll talk about that. What are the different kinds of data you have in astronomy? There's the economic value of the data, and then the speed of the data generated. This is also very important, but it also applies to more of these commercial things. So let us, for example, all of you all have heard about the Event Horizon Telescope, and now the amount of data which was there from Event Horizon Telescope was about 5,000 terabytes. Okay. This is larger than the New York Stock Exchange in 13 years, okay? So if you were to upload the data, you'd take 44 years and about 22 years to download the data. And therefore, actually, you all must have heard out, it sounds very primitive, but what they actually did for the data is that they physically transported it. They actually had it copied onto hard drives, and the hard drives were transferred to the places where the analysis was done, right? This may sound primitive because, you would say, why not do it online? But because the data size is so large, it would have taken too long. So they actually physically, you can see, many of you all know her, I'm sure, right? Yeah. What's her name? Yes. She got very popular after the Event Horizon Telescope, right? And she was one of the students who worked on the data. And you see, this is her thrill when she actually received all the data. Now, there's a bigger problem with space telescopes, because of the size of the data and stuff like that. And then Margarita spoke to you about this is what is going to happen very, very soon. This is the Large Synoptic Sky Survey. Now, earlier what happened in astronomy, people were basically just scanning the sky, right? So you had different kind of surveys of the sky in different wavelengths, right? From optical, ultraviolet, X-ray, whatever. You surveyed the sky in different wavelengths. Now, what is interesting people now is the transient sky. Okay, about the objects which change in their brightness. And that is what this telescope, this is the Vera Rubin telescope, and what it's going to do is what is called the Large Synoptic Sky Survey. So the idea is you are basically going to scan the sky, right? And you'll do the entire sky every 3 nights, right? And you're basically going to look for transients. Now, these transients can be various kinds. They can be supernova, kilonova, they can be all kinds of transient objects. All of them have a different kind of astronomy, astrophysical importance. And if you see over here, you're getting about 15 terabytes per night. Okay, that's the kind of data which you're going to be getting from LSST. And then Rita spoke to you also about the SKA. This is the Square Kilometer Array. This is a radio telescope which is being built. It will be operational by the 2030s, and it's across 2 different continents. There's the set in Australia as well as in South Africa. And this is supposed to be giving you can actually count the number of zeros you have over here, right? That would actually help. It's 2 into 10 power 8 zeros with petabytes per night. That's the kind of data which is going to come very soon. And therefore, like I told you, is often what is being done in many of these data sets is that you actually bring the code to the data. So people are allowed to query at the level of the server where the data is sitting over there. And then you query it, and based on the conditions, whatever you do, you actually then retrieve the data you need, right? Now, what is astronomical data, right? This is an antique, the position of constellations. This is, people have been marking constellations, right, since a long time. And the earliest catalog was that by Hipparchus. And you can see it over here where you have the zodiacal constellations, right, which mark the track of the sun, and totally 88 constellations with this thing. Now, in present day data, what do we have? This is basically digital data. You have either you could have in-depth study of individual objects, right? You could be using Hubble data, James Webb, whatever, where you have in-depth study. But that is done from what are called observatory class telescopes, right? Which are looking at targets, which is typically what, oh, I pressed something. What is, okay, oh God. I pressed something with my hand. ये क्या प्रेस हुआ? ये क्या गलती से मेरे हाथ? Yes. And what you have, the other kind of telescopes are what are called survey telescopes, which keep scanning the sky. You don't have a target. Okay, thank you. Okay, so then you have the survey data, which basically keeps scanning the sky. For example, LSST, or for example, if you have Gaia data, or you have 2MAS, these are all survey data, which keep scanning the sky. And then you have various other data sets, which are this thing. You also have simulations, right? In astronomy, a very important role is played by simulations. What you do is you basically feed in your formulae, your physics formulae, and your physical laws, and then you simulate the universe, right? Because you cannot observe it at the scales of millions or billions of years. And therefore you simulate, and then you compare your simulations with the observations which you have from whatever data set you this thing. And then there are various data centers. A lot of data centers provide Jupyter notebooks itself, where they actually show you tutorials where you can use it to learn how to analyze the data, right? So the starting steps are already provided, and what you can do is, as you use that to build on it further. Now, in astronomy, what are the types of data? Obviously, the simplest type is the images, right? Which are this thing. Then you also have what are called catalogs, right? Which are in tabular format. You have spectra, you have time series, you have simulations, you have polarization. So the different kinds of data sets which we have in astronomy. So depending upon the kind of objects you are interested in, you can select the types of data that you this thing. Now, what is the power of big data? Basically, it's freely available. Yeah, that's the most important thing, that with this kind of archival data, right, which is available on the net, this is freely available for everyone. It's easily accessible, and it's the best quality data, right? For example, if you're using Hubble data, right, you could not get data better than that. And it's all available. So if you're using Hubble, Gaia, Kepler, TESS, whatever you're using, Spitzer, it's the best quality data and it's freely available for you, right? Even the James Webb, there's already a lot of data already available of James Webb. Some of it is proprietary data. If people write a proposal, then for a certain period, the data is theirs. But after the proprietary period gets over, if it varies for different observatories, then again, it's available to anybody to use and you can actually use it. There are also a lot of data and image analysis. I think we can try putting off these lights. Yeah, so this is a little too light. So you can see that along with the data which is available, there are also data and image analysis facilities. And then there is also what is called the virtual observatory. We won't be talking too much about that today, but that's also very important because these are tools which are provided to analyze data, which are using very user-friendly methods. You know, they can be even done by school children. We don't need चलता ठीक है कोई बात नहीं. Okay, and then there's statistical analysis. We'll be covering that tomorrow, a little bit of stats also, and then maybe a little bit of machine learning also. And the idea is, see, earlier science was hypothesis driven, right? I have a hypothesis, based on that I build a picture and then I see my observations. Now in this case, what we are doing is more of data driven research, right? In the sense, you have data of certain objects, you analyze that data, using that you get some patterns, and you use that to actually understand what's actually happening, right? So the approach itself is quite different. Now let's look at, first of all, our astronomical images, the digital images that you have. These are basically two-dimensional arrays, okay? Now what you have is, this is like a matrix, so the CCD, or the charge coupled device, is basically made up of pixel elements or pixels, right? So typically the CCDs could be 4K by 4K or whatever size it is. And for each point, you will have a certain count. So what you basically have is, you have a 2D array with pixel value brightness, okay? So when you're handling any astronomical data, you basically have to handle images like this. And this follows basic matrix arithmetic. For example, you can use this to add two matrices, you can subtract them, you can divide them, you can multiply them, you can do various things about them. And if you go into image processing, you will see how is it, when and how do you need to subtract images or add them or multiply them into some factor or whatever, right? So that is essentially what is done, which we have in the astronomy images. Now, okay, okay, yeah. The other thing is that all these images, the beautiful colored images which you see, they are basically artificially created images, right? So what you have is, when you take an astronomy image, you basically have a filter over this. So there's a blue, green, red filter, and these give you what are called your RBG images. You have the counts in different filters, and then you add it to make up a combined image, right? And that addition is done using basically artificial colors. Often the colors are related to the wavelengths, in the sense, shorter wavelengths will be blue or purple. So for example, X-ray light would be blue or purple, while infrared would be red in color. So you artificially add in those colors depending upon the wavelengths you are considering. Now your images could be either point sources or they could be extended sources. Yeah. And I almost started talking to you all about what are called CCDs. So the very big revolution in astronomy images came with the Hubble Space Telescope. When Hubble Space Telescope was being launched, they basically needed to design cameras for the telescope in which you could actually get these digital images. And here you see, this is Boyle and Smith. These are the two who are credited to be the inventors of the charge coupled devices. Now charge coupled devices are everywhere, or our phones, our laptops, everything has these digital cameras, though this was, like I said, it was initially just done for the Hubble Space Telescope. And now what happens is on this, you basically put in filters, right? So what does it do? This is basic photoelectric effect. You have light falling onto this grid, and based on that, you develop a certain charge, and you basically measure the charge. So it's an electronic device. And what you have is you have different filters placed on the pixels, and based on that, the pixel is sensitive to a particular range of wavelengths, right? And like I told you, now in today's times, we have it in all digital cameras, camcorders, scanners, etc. All of them do these colored images, these images based on this. Now, when we basically do astronomy imaging, we will show you a little bit of that too, using robotic telescopes on day 4. What you basically do is you take images of the same part of the sky with different filters. Okay, what is a filter? A filter is, it basically permits light of a certain wavelength to come into it with a certain width. So you have a certain central wavelength and a certain width in which you can permit the light. And you say do it with a blue, green and red filter, and you use that to actually create your RGB images using artificial colors. So typically images like these, which you can see over here, these are using artificial colors, right? You're basically using the filters, using artificial colors to actually get these kind of images. In astronomy, images are stored in a certain format, which is called the FITS format, which is the Flexible Image Transport System. Okay, you need to be aware about this because when you are handling these images, for example, in a Jupyter notebook, you have to read FITS files. Okay, now FITS later on was extended for more. It was initially only meant for images, so it would have the pixel values and it would have what was called a header file. The header file had information about which was the telescope, what was the exposure time, what were the filters, all details about the images. And so you had the filter, the header file combined with the pixel values. But now FITS has been extended to even you have tables in FITS format. Again, so if you have catalogs, which are tables, they also have some additional information about them, which does that. And then FITS was like it was designed specifically for astronomical data. So all the software which we use in astronomy imaging, they basically handle FITS data. Okay, you will see that, for example, you may be aware of JPEG files, BMP files. These have much lesser information than that's what's sitting in a FITS file. So if you want to look at a FITS image, you basically need to have a FITS viewer either in your Jupyter notebook or as a display. And that would be necessary for you to, okay. Yeah. So, it's also FITS is also used to store non-image data, for example, spectra, all these other kind of data also. So it's been further developed. You could actually have what are called data cubes and different kinds of things. So we won't go into these details, but basically FITS has been extended from the basic style to include many more kinds of objects, but essentially for this thing. Now the brightness also, you will see, maybe we may not get too much of time, but when we use these visualization softwares, you may actually have different ways of, in astronomy, a lot of work is done in what is called image processing or image visualization enhancement. You may look at the same part of the sky, for example, this, where you almost cannot see anything. But then if you actually change the brightness cuts, etc., you can actually see it to this precision. This is the same image. There's no extra information. It's the same image which is being looked over here, only that you are changing your cutoffs. So for example, the left one you see is linear scaling. The second one is if you do linear scaling, putting some cutoffs. For example, it's given 4572 and 6002. And then there is something called square scaling. That means you get the pixel values here and then you square the values, you can do this. So there are many different techniques used in astronomy to actually enhance images. So like this same image can look like this, which also already gives you much more information than this image, right? So there's a lot done about that. Here is an example of a composite image of this cluster called NGC 281. So what you're seeing in the background is actually an image which is in infrared, which is from Spitzer, okay? And then the purple part, which you can see, this is the image from Chandra, which is an X-ray telescope. And therefore the Chandra part is all in violet, but the Spitzer part you can see is in red because that is in infrared. So that's the Spitzer image, which you can see, and it has been added on with the Chandra image to give you that image, right? So, sorry, this image which you are seeing is the result of you adding this Spitzer image and you're adding it to the Chandra image. You have to very perfectly overlay them so that they correctly, all the pixels are aligned correctly, and then you can get an image like this, which is that composite image, which gives you Chandra with Spitzer, right? And now these are very important things because in astronomy, when you're trying to understand objects, etc., I want to see which are the parts which are giving me X-ray radiation, which is giving me infrared radiation, and different details like that. I may want to do things like that. The other kind of data we handle in astronomy is what is called spectral data, right? You all know what is spectrum. You basically have intensity versus wavelength. So you are looking at the light coming from a source and you are trying to see what is the difference in intensity at different wavelengths. So in principle, this is a one-dimensional data. It's giving you the energy distribution over different wavelengths and the contribution of light. And basically, this is very important because it is a chemical signature of the region you are observing. So if there's a region you are observing for which you have spectroscopic data, that's really very useful because it directly gives you the chemical. Once you identify these spectral lines, right, you can use that to exactly match with and get the chemical composition of the region you are trying to study, right? Now, often what is done is these are what are called data cubes, the spectral data. So you may observe at different wavelengths and you can actually stack your spectra. So this is like stacking the spectra. So the same region, I'm going to see it in different wavelengths. These are bluer wavelengths, greener wavelengths, redder wavelengths. And the data is often stored like what is called a data cube, which is in principle three-dimensional data, because it's giving you the same part, the same object in different wavelengths. It's giving you their spectra, right? And this is often done in what is called integral field spectroscopy, when you're actually wanting to study different regions. Supposing there's a galaxy and you're trying to study its rotation, right? So you will actually, some part of it is going to be blue shifted, some part of it is going to be red shifted. So you want the whole galaxy and you want to stack up those regions so that you can then figure out which is the part which is coming towards you, which is going away from you, and then if you can get the delta lambdas, the difference in wavelengths, you can actually measure the velocities, right, with which it is rotating and various details like that. And therefore, what you're getting is from each pixel, in principle, see if I were to make a cutoff like this, right? This is actually going to give me a cutoff along wavelengths, right? This one, each slice is basically a slice in wavelengths. But when if I drill a hole through this, for example, I'm going to get the difference in intensity from blue light right till red light, right? So I can get it in that. So each pixel gives you the whole spectrum in principle. Now, what was here? I don't know. Okay, let us leave that. Okay. The other kind of data which you also need to handle is the catalog data. That means you have data in the form of tables, right? So when an astronomical image is analyzed, you may then list the sources which you have. So typically you can see over here, there is the RA, there's the DEC, there's the galactic longitude, latitude, there are various parameters. So you may actually create catalogs, right? Now to handle catalogs, these could also be in FITS format, or there's what is called the VO table format. It could be in CSV format, in different formats. And there's different software available to actually handle these formats. But typically in Python, you can handle all these formats. There is what is called AstroPy, which is a package specifically in Python for astronomy. And that will help you handle all kind of catalog data, right? Okay, so we'll be seeing a little bit of that too, right? Another very important kind of data you have is what is called time series data. In time series data, what you have the change in brightness of an object with time, right? So I will be doing that with you all when we'll see Kepler data and TESS data. Now, Kepler and TESS, these were two satellites which were basically sent to study exoplanets, okay? Look for planets in other systems. And how do you basically identify exoplanets? You identify exoplanets that if you are looking at a star, right, and there's a planet which is going around it, then when the planet comes in front, the brightness from the star is going to dip, right? So you'll have a dip in the brightness, and then the star you see, and there's a dip in the brightness. And the dips can also, there are many details. The simplest thing is you look for these dips. These are called light curves. So we will see light curves for Kepler as well as TESS. And you can see that the simplest thing you can get with the light curve is you'll get the period, right? Other than that, obviously, there's no reason to assume that it's going to be a single planetary system. Your system could have any number of planets. Depending on that, your structure of the dips, etc., will also vary depending on how many dips you're getting, depending on how many planets are there, what are their sizes, etc., right? Also, depending on the atmosphere of these planets, you will have different kinds of structure over here, depending upon how the atmosphere lets light move through it. So we will do basic time series analysis for Kepler, but obviously there's a lot you can do in the details, right? There's a lot of details you can do with which you can study the time series in a lot of precision. A standard technique which is done is also what is called folding. That means you get a pattern. Yeah, you get a pattern, but to improve your statistics, you actually fold the curve, right? You fold it and you add it on together, so that then you get better signal to noise, and you can actually look for more detailed structure on the time series. So that is for exoplanets, but time series data is obviously used for anything and everything which is variable, and we know that most sources are variable sources. So you'd have different kind of variability signatures depending upon the sources. So even Rita was talking to you about grav lensing and globular clusters, etc. So typical variable stars have kind of signature light curves. Looking at the light curve, you can easily this thing specify what kind of a variable star it is. Or similarly, for example, if you have a microlensing event, right, then it is just blocking of the light. There is no physical process which is happening, which is causing variability, and therefore you can actually look for symmetry in your light curve. So the light curve analysis is something very, very detailed and deep, on the basis of which you can do a lot with that. We'll do a little bit of this. Right. Now, what are the different tools? So we were talking about virtual observatory, and there's something called the DS9, Deep Space Nine, which is basically with which you can observe, visualize astronomical images, FITS images. We can show you how to install that. Today in the afternoon session, we'll have a talk after lunch. And then after lunch, what we are going to do is we are basically going to handle all the software installation, right? If the software is all installed, then we'll start off with the Python. If not, today we'll just help you all install the software that's required, right? So we'll install some of these softwares as well as this thing. But obviously, they're not to be used as black boxes and this thing. Now, there's a lot of metadata also along with the data, which couples the data, which is descriptive information about the data. So whenever you're taking data from any data archive, you need to carefully check the metadata, which is a description about the data. In most of these websites for archives, you'll always have the caveats in the data, right? What are the things you need to be worried about, right? For example, with Gaia data, bright sources are bad, because basically Gaia saturates with the bright sources. So for the bright sources, you have to use some other sources. You cannot be using that. That will not do it well. Similarly, for different data sets, you will be given, there are instructions, details as to what are the nuances that you need to be careful about. And we'll see some examples. So essentially, what's an astronomy archive? It's organized, systematic information about the sky, which is this thing. And like we mentioned, today's archives are terabytes, petabytes, they're very large in size. Now, I was talking to you about Hipparchus, who actually had his first catalog, which had 850 stars, which ranged from 1 to 6 magnitude. I hope everybody knows what's a magnitude scale. Does everybody know what's magnitude scales? Right? So in astronomy, we measure brightness using a unit called magnitudes. Okay. Now the thing is that as magnitudes increase, an object becomes fainter. So our naked eyes look for typically 1 to 6 magnitude. And now we do not even see this with our kind of skies. But once upon a time, people could see that. And so these are all naked sky observations. Hipparchus, and then Tycho Brahe also had his positions with naked eye planets, which were used by Kepler. And so actually Kepler is one of the first examples of user of archival data, of using it for doing science, right? Now, after that, there were various different catalogs made for stars. There's a Bayer's catalog, star catalog, and then in 1771, Messier made a catalog for nebulous objects. See, at that time, this is when telescopes just came in. Many of these objects were just some kind of nebulosities, and people had begun resolving them to actually check out whether they are genuine nebulae or whether they can be resolved into stars, etc. And based on that, they started cataloging it. So you had, for example, the NGC catalog, Messier catalog, various catalogs which were made, right? Now, one of the standard catalogs, if you actually, I should have mentioned Aladdin. That's also a very important software which is used to visualize astronomy images. Rather, if you want to look at any part of the sky, you can use this tool called Aladdin. And one of the standard things which you will see, which of the images of the sky, is what is called the DSS, or this is from the Palomar Sky Survey. So basically what happened in the 1950s, you actually had 2000 photographic plates of the night sky, each covering 36 square degrees. And in the 90s, this actually got digitized, which is called the DPOS. And typically with Aladdin, for example, if you want to look at any part of the sky, you can actually get the DPOS images because it's there. It's an all sky survey, right? But gradually, that was the DPOS, but then you had digital data coming up. This is the CCD, right? Those were photographic plates, which we were looking at. And, oh no, yeah, these were photographic plates, but then gradually you had CCDs coming in and a lot of technology. So you can see that the kind of data, we don't have time to talk about this, but CCDs are very important. Number one, for what is called their quantum efficiency, the efficiency which is this, as well as what is called their linear response. So there is a, see what happens with photographic plates is that they saturate after a certain point. So you cannot go on exposing it. But in CCDs, you could have very long exposures because you could have a good range where you'd have linear response. And then you could take a lot of images, stack them up, and actually get very deep images of the sky. So CCDs, therefore, they are useful for these various things. Number one, for their sensitivity, or what is called their quantum efficiency. They have about 80%, depends on how you this thing it. Then they are linear detectors, and they have a very large dynamic range. By dynamic range, you mean the faintest and the brightest. It can do it very well. So here you can see in this plot, this is our eye, which you can see. This is the wavelength in which we can observe. That is the optical part for the eye. The photographic plate is also shown over here. But you can see with CCDs, there are different kinds of improvisations done to them. There are what are called thin CCDs and various things with which you can actually look through a much larger range of wavelength with a very good quantum efficiency, okay? Quantum efficiency is telling you that, for example, if there are 100 photons, how many of the photons do you actually detect? How much does your detector do? So you can see the eye is barely, it's really very, it's small, but when you're going up to CCDs, you're going 80, 90%, it's far better, right? And then a lot of other things is that we also need to look about other wavelengths too. There are similar growth not only in optical wavelengths, but also, for example, in radio wavelengths and X-rays, etc. There's a lot of technology which has been part of this progress in actually, improving our sets in this. So, like I mentioned, astronomy archives are very good because they are in the true spirit of science, where in principle, the data is available to everyone. You do not have to get permission to use the data. Just for the proprietary period, there could be a problem, but certain data sets, for example, Gaia data, if you deal with Gaia data, there's no proprietary time at all, okay? They get the data and then there are data releases which are released all over the world at the same time. And therefore, it's available to everyone. And that becomes very useful for us, especially when you do not have access to such large telescopes. See, in India, the largest optical telescope is a 3.6 meter telescope. While all over the world, you had 10-meter telescopes like, a long time back ago. So we are, in that way, we are, lagging behind in our kind of optical telescopes, definitely. But here, what happens with this, you can actually have access to the best of telescopes, the best of data, and that's this thing. And then just for even non-science people, there are a lot of citizen science projects in which you are actually again using this very good quality data, right? Where people who are not science students also, they can actually contribute to these citizen science projects. We will not be talking about this, but this is just for your awareness that there are various ways in which, since there is so much of data, it is also being opened up to people or citizens who are non-science people who would like to contribute. So they can do various things. For example, classifying morphology of galaxies, right? There's a project called Galaxy Zoo with which you can classify galaxies. And if you classify a certain number of galaxies, you get certificates and things like that. There's also what is called planet hunters. Basically, again, you're looking at Kepler test data. You're seeing their light curves, and you are actually using that to distinguish whether there are exoplanets, etc. Right. Now, there was already a question somebody was asking, which are the various data archives? So we'll be looking at all of these, hopefully, some of them. So there is what is called Vizier. Okay. So Vizier is basically access to catalogs as well as data tables of published data, right? Supposing I observed some object, right? And based on that object, I built a catalog. I looked at a star cluster. I made a catalog of all the stars belonging to that cluster, etc. And I published a paper on that. So then I upload my data to this place, Vizier, and for the corresponding paper. So if somebody wants to even work out my whole paper or wants to replot my figures, right? They can actually access the data because the data is available on Vizier, and they can analyze it, either use it to learn it, or they could actually use it to critically assess my data. So for example, many of you all would have heard about the detection of phosphine on Venus, right? So when phosphine was detected on Venus, the lead authors of the papers for phosphine, like it's done in to this thing, or the data was provided, right? And then there were groups who actually contested this group using other techniques. There are different techniques for data analysis with which they contested the lead authors that the results you have got are not you know there's something wrong with your analysis or something like that. So the idea is very, very good. Number one, you can use it as a learning exercise. If there's a paper published, you use that, bake their plots, do things like that. You could also use to understand the data analysis techniques, or if you can think up some kind of a change or an improvisation of the techniques which those people have used, right? You can actually use their data itself and show them how with their data they can get some other results, right? So similarly, not just for phosphine, even the LIGO data, a lot of the data is all available on Vizier, and you can use that. You know that in many of these things, they use different machine learning techniques or template fitting techniques, various kind of techniques. So you may actually think up an improvisation or a flaw or something like that in that, which could be done directly with Vizier. Simbad is another database which actually provides data. So you give any part of the sky. I'll show you these things online. You can check it out. If you do Simbad, you can actually give a part of the sky, and it will tell you everything that lies within that, as well as the references for it, etc. There's also NED, which is the NASA Extragalactic Database. We'll see this site also, where again you can get a lot of, it's more on whatever parts. There is the Sloan Digital Sky Survey, SDSS. This is data release 4, but now it's already data release 17, I think. It's already 17. This is again, it is, but the Sloan Digital Sky Survey is not an all sky survey. It's only a quarter of the sky, but it has very good data. There is the TUMAS survey, which is a survey in the infrared, which covers the entire sky. This covers the entire sky in the near infrared bands, which is the J, H, and K bands, 1.2, 1.65, 2.2 micrometers. Those are the things. Then even ESO, the European Southern Observatory, they have their archive where they are very good telescopes, and each of their telescopes, when you check up the data archive, you will see data from their various telescopes, and that can be used. Then there is the MUST, which includes the this is multi-mission at Space Telescope Science, This has not only HST data, but it has Kepler, it has James Webb is also there over here, and you have Galax and a whole lot of these things. There is the 2-degree galaxy redshift survey. There is the IPAC. This is for the infrared, this is infrared submillimeter, NASA, and then there's the Hubble Legacy Archive. So this is just some. There are many, many more. So specifically for the objects which you are looking for, you will actually have to search and find what are these things. So for example, this is the site, the Hubble this thing. And like I told you, you have it for Hubble, you have James Webb, you have TESS, you have K2. K2 is the next version of Kepler, the warmer Kepler. And you have all these data sets which are sitting over here. So if you want to work on James Webb data, you'll just have to go here and get the data from there. So it has all this, not only the data, it also has virtual observatory tools, it has source catalogs, and it has various other things that can help you to this thing. Then there's Gaia, which is a catalog, which is a European Space Agency satellite, basically meant to study the stars in our galaxy, 1 billion stars, with very, very high precision. So basically you are very well measuring the positions, the RA, the deck. The parallax is a measure of the distance, 1 upon distance. This is the radial velocities. And then you're doing the proper motions in RA and the proper motions in deck. So this is the Gaia, this thing. We'll have a tutorial on Gaia. And yeah. Then I hope you all have heard about the GMRT, which is the Giant Meter Radio Telescope. This is located close to Pune. And you can actually use the online archive. Again, they follow a system of proprietary data. So this is an observatory mode. So people who've proposed and got the data for a certain period, the data is blocked. But after it finishes, I think it's 18 months. After it finishes 18 months, then you can actually put in the proposal code and you can actually download the data. So if you want to deal with radio data, you can go to the GMRT one. If you want to deal with X-ray data, there is the Chandra telescope, which is the best source of X-ray data. So you can actually go to the Chandra data archive, and there are various ways of querying it. It also has a point source catalog. There is a point source catalog of Chandra. So if you actually look at a certain region of the sky, it will give you all the sources it has over there. And there are various ways of actually querying the archive and doing it like that. Okay, then the SDSS survey, this is the Sloan Digital Sky Survey. This is a very well-known survey. And like I said, though it's not the whole sky, it's a quarter of the sky. But what it has done is it has studied this whole region in very, very good detail. So you have photometric as well as spectroscopic data of this thing. And for about 3 million objects, and a lot of very good useful data is there in Sloan Digital Sky Survey. Then this is the one that we are looking forward to, the Large Synoptic Sky Survey, which is going to come up soon. And soon you'll have this data also. This will also be immediately available for everyone. So basically, it's an 8.4 meter telescope, which is going to give you data in 6 spectral bands, which, in 6 spectral bands. Each of them, each tile or each field size is 3.5 square degrees. And that will be for LSST. So we will also touch a little bit upon this, as how do you actually use these large data sets. So like I said, now the way we are looking at science is more of data-driven science, where you actually, supposing you collect a whole lot of data about planets, for example, exoplanets. Now you use that data to actually look for patterns, correlations, classes, etc. in the sample that you have collected, right? And that's when so what are you going to use? You're basically going to use visualization tools. You're going to use data mining tools, because when you're picking up your data, right, you're going to put some criteria, which could be on the quality of the data. It could be on the location of the data, the region. Supposing you're looking for planets only around G-type stars, right? It's like the sun. Then you'll typically query your database for those kind of planets around those kind of stars. Then you'd use some amount of mathematics, some amount of stats. You may also use some amount of machine learning, deep learning to analyze your data. And hopefully your data should give you some good results, right? Now, there are various data mining tools which can be used, which will be used for classification, regression, clustering, outliers. A little bit of this will be touched upon on day 4. The virtual observatory, which we'll talk a little bit about it on this thing. And then there's also literature survey, which we will also try to show you a little bit of how can you actually look for literature. Now, in astronomy, there's what is called the ADS, so there's the Astrophysics Data System, and you can actually use that to query literature about objects of your liking, right? And that is very important because there's obviously a whole body of work done on whatever you are trying to study, and it is important for you to actually check up what is done, right? So you actually do that using that. You could also use various things, for example, machine learning. On day 4, student presentations, Mudassir, who's soon going he's going to soon submit his thesis, yeah, on machine learning with Gaia data. He will show you some of the stuff he's done. Seth will also show you, both of them are my students. And if there's anybody else, we have a special session for student presentations, right? So please, if there's anybody who has something they would like to present or share with the others, we can't give you a very long slot. We'll give you like 10-15 minutes. But if there's any student who would like to present something, please do come to me, and we'll fix your things all on day 4 on Friday after lunch, before we have the valedictory, right? So if there are, we'd like to hear from you all also, if there is something that you would like to share, so we can actually do that. Yeah. So I'll end with this. This was just a brief overview. We will be, during our sessions, we will, what do you say, talk about fixed data archives, like I will do Gaia Kepler tests, but others will cover other these things, and let's see how it proceeds. Yeah, thank you. Yeah. Questions, please. Yeah. Yeah, afternoon, like I told you today, afternoon, after that Snehanshu Saha talk, we'll have a talk. And then after the tea, then we'll be basically focusing on all your software installations, right? First you'll ask questions and we'll, yeah.
Thank you, ma'am, for the talk. Ma'am, I have a question that suppose we have some structured data. So on the structured data, we can do statistical analysis, any kind of data mining analysis we can do. But my question is in regard with the unstructured data, how we can analyze that, how we can because it is totally unstructured, how we can figure out something from that.
I think your only choice is to structure it, right? How do you handle unstructured data? I think you have to structure it only. Because if you're running any kind of software, it'll want it in a certain format, in a certain this thing. So, what do you say?
Yeah, and then most
You have to structure it. Otherwise, it won't be able to do it.
and
I don't think.
data which is being provided, it is
Yeah, but what you get from the archives, all data from archive is structured. What would be unstructured would be if you did some observations, right? Then maybe that you have not structured it. But I think there's no choice, you just have to structure it. I don't think you can do anything if it is not structured.
And then if you have observed from some observatory, then there they have a pipeline of cleaning it. They'll tell you what are the issues with the system, what is the seeing, all the details are there with which you have to do the cleaning and everything. So you need structure.
You have to structure it. Otherwise, you can't. Instead, a lot of the effort in virtual observatory was about structuring data, of putting it in a format which is, which can be done with any wavelength range, right? And for example, I'm an optical near-infrared astronomer, but I should be able to even handle radio data or X-ray data because it should be in such a format which I can handle. So I think a lot of effort is put into getting structure because that is important.
The Virtual Observatory Alliance, there are a lot of countries who joined together and they worked on the protocols, how data should be shared in what formats. And they've all come up with an agreement that if data is being shared by an observatory or it is done in a specific way. There can be difference between radio data and optical data. But then there is a standard, they have defined the standards, the protocols, which they do it. So, yeah, unorganized data is, you just can't handle, right? You have to, so cleaning, most of the time the data which you get, it has been partially cleaned and then the header file of the, gives you more information if you need to know more about it. So we may see those, some of the fixed files we
Yeah,
can
it's
download and show you how to see uh, the nuances, what are the things that are exposure time, filters used, back pixel mask, the CCD had some back pixels. So all those are there so that you can use that information to make it more meaningful or make it efficient. I think we are quite on
we are
time.
perfectly on
How
time.
many of you are
Yeah.
absolutely new to Python? You have never used Python or yeah, you've never. Okay, so they're small. And how many are experts, geeks in it who are extremely good?
I mean, you've done a PhD thesis based on Python notebooks or doing it.
So those who are good, you can help us teach others. And then they may be, see actually when we go down to, so after how many of you have Python running on a